Hello, I'm Rybka from the University of Washington. Thank you for having me here. I didn't have a great title slide, but I did get a good picture of the rain rolling in over the city from the Bobley Gardens. I'm giving two talks today. I'm going to try and keep them pretty separate, and I'll each about half and half. The first one is about the US axion program, in particular this snowmass process, and I'll explain to you. Maybe grad students can fall asleep for this part. It's a little political, but still, I wanted to share it with you. And then the second half, I will talk about specifically current status and future plans of ADMX. So let's begin with the US axion program. So this is in the context of what is called the snowmass process, which in the US, every 10 years, all of high energy physics gets together at a meeting and writes a bunch of white papers. Well, first it's letters of interest, then it's white papers, and combines all this information to advise the US funding agencies where they should be putting their money over the next 10 years. In particular, snowmass gives just a list of here's the interesting physics out there. And this is fed, these reports are fed into what's called the P5 Particle Physics Project Prioritization Panel that actually says, here are the funding priorities. And this is important for us because when we write our proposals to like the DOE, there's a question saying, is your physics in the P5 report? And if you say yes, then it is just ranked higher automatically than saying no. It's a higher bar. And so this culminated, it was supposed to be in 2021, the pandemic put it off till 2022. We had in summer of 2022, a meeting, this time it was at Seattle. So you get a sense of the scale of the number of people just involved in the in-person, and this was the culmination of many Zoom meetings. So where do axions fall in all of this? So for the first time, axion is first times as compared to like last decade, axions had their own subgroup. There was a subgroup of wave-like dark matter. It was a subgroup of the cosmic frontier. There's these various frontiers, cosmic, intensity, energy, things like that. So the people trying to wrangle the community within this subgroup were Lindley, Winslow, Jörg Jäkel, and myself. And so I'm sharing with you the information we assembled as, talking to the community, trying to get something a story everyone could agree on. So the story is old to you, and some of you may disagree with, but it's important that I share it with you so you know what people outside the field have heard. And so that's your starting point when trying to convince them that you need funding, or this part is interesting, or that you disagree with everything. So I start with just some of the documents produced. So we produced these community white papers. First, there was a large number of letters of interest that anyone could solicit, or it was solicited, anyone could contribute. And we tried to gather these into two community papers with large author lists. One was focused on axions in particular, and one was talking about everything beyond axions, scalars, vectors. You're welcome to read these. These were then fed up the chain to the frontier, to cosmic frontier. So this is WIMP dark matter, dark energy, whatever astrophysics should belong in high energy physics, which is debatable, into the cosmic frontier report. And of course, every time you go up the chain, the message gets simplified. And I will explain that this plot made it up the chain. I'll explain that. And the message, we have to give these catchy slogans because it's read not only by physicists, but it's also these maybe just the first lines are read by senators and things. So we want to delve deep. So that's going down in looking for the QCD axion. And that's to say that there's many ideas of axions and axion-like particles, and here is a benchmark that we feel is achievable to shoot for in the next 10 years. So it was delve deep and search wide was the phrase. This then frontier report was mixed in to the grinder with the other frontier reports to one snowmass final report. It was 75 pages, and axions made it to page 11, which I feel is quite an accomplishment given that there was very little mention in last decade. There are several axion experiments mentioned by name. You can dig this up on arXiv and see. So this report was then sent to the Particle Physics Project Prioritization Panel, which is supposed to take the opportunities and rank them. And so this process is still going on. though I hope my part has ended in it because I'd like to get back to doing some physics for a while. But I will share with you the slides that I was invited to go and talk at this town hall, and I will share with you the slides I shared with them. So I opened by talking about wave-like dark matter candidates. This is fairly new in the last few decades, and we chose arbitrarily the definition of masses below 1 eV and masses above the eV were sort of particle-like. Point out that they can be scalar, vector, and pseudoscalar, and the important thing is that we've got a benchmark, a famous candidate that is the QCD axion. So then just some fun facts about talking about how the de Broglie wavelength gets big, the number density gets dense. Ben, I suppose this slide came from you, and some Lindley processed it, and then I processed it. And then for many in the community don't even really understand what it means to be detect wave-like dark matter. So we had to talk about how most axion and axion-like experiments care a lot about frequency. That is to say, in some noise floor, if you zoom in, axion signals are bumps in frequency space. So much like a radio wave. It's worth pointing out, so how important are axions to the community, particularly in comparison to other things? This is thinking about prioritization, and this is a great slide from John Ulay showing archive mentions of axions and WIMPs in archive, and you can see nearly 2 decades ago, it was clearly WIMPs were the predominant interest and of course should receive the majority of the funding. However, in recent times, axions have gained popularity and are on par with WIMPs. And here's the point where I argued, well, so surely our funding should be commensurate, though this drew some laughs from the audience. It's there's a certain amount of momentum that one has to overcome. However, this justifies saying funding agencies should be paying as much attention to axions as they should for WIMPs. I then, of course, had to explain the motivation. The QCD axion is very straightforward, where one can point to a measurement, the neutron electric dipole moment, point that it is anomalous, and then say there are several explanations for this, but there's really only one good one, and that is the QCD axion. We point out that the QCD axion could, and in fact should, be formed in the early universe. It's important to note when you're talking to people who work with WIMPs or working outside dark matter entirely, who have this very thermal production model in their head, that axions do not work at all that way, that it goes from being a field to being a dark matter rather suddenly, but very, very early in the universe. And then not only this misalignment mechanism, but there's string and defect decay, which are rather complicated to explain to a general audience. So there's the question of where to look. While the QCD axion has a fairly narrow range of predicted couplings, there's a wide range of masses. We've heard many of them earlier in this 5-week program. In general, it's useful to talk about how more massive axions tend to happen after inflation and less massive axions tend to happen before inflation. As a general principle, the discovery of almost any mass, there will be at least one theorist who says, I knew it all along. And so as a consequence, our strategy is to, one, look under the lamppost. If you have a technique that is capable of being pushed to reach the QCD axion, that technique should be pursued. It's got a shot. Meanwhile, build brighter lamps. If the axion is not found at first at some mass ranges, there will be many people who tell you need to move to other mass ranges. And so we should look for ways to explore the entire mass range over the next decade. Here, you've seen this Lagrangian many times. The way we split this up was to say the axion-photon coupling, at least from the perspective of can you get to the QCD axion, the axion-photon coupling has a very clear experimental signal and has been very well studied, while the other couplings are interesting, important, and have promising experimental techniques under development. Though there aren't like existing experiments that are hitting the QCD axion with them, and so those need to be pushed forward, developed. So here's a representative plot showing axion-photon coupling versus axion mass. It's easy to point out the QCD axion has a relationship between these two and lives on this yellow band. And there's many things that search for axion-like particles. And there are a few things that are reaching down into the QCD axion. So there's a lot of parameter space to explore, both in the yellow band and both outside. You've heard, I guess this is now out of date, right? These are creep. It sounds like these are quite creeping down. And then the cutoff here is somewhat arbitrary. Below here, we get into interesting things like black hole superradiance. But it seems experimentally, if we're talking about within a decade, for ground-based experiments, this is the accessible region that we could conceive of. So talking about what is the next decade looking forward in a very simplified, a simplified plot that the accelerator jockeys can understand. We talk about this mass range, so we've just collapsed down onto the QCD axion scale here, and we say, well, at very, very low masses, we begin having exclusions from black hole spins, and at very high masses here, we begin having exclusions from astrophysics, and this whole range is what we need to be building experiments to look for as axion dark matter, and there exist a few haloscopes that are excluding or have sensitivity to axions in these mass ranges at either the DFSZ or KSVZ coupling. As for the near future, there are proposed experiments, and you'll hear more about these. This is DMNI's dark matter new initiatives, and that's a program run by the U.S. Department of Energy to sort of foster the next generation dark matter experiments. And so both of these are things sitting in the queue that have preparatory funding to begin as projects. And one of our messages was, yes, continue doing that. And so we said, look, we have good job, funding agencies. You've already got projects in line to study this range, but this is not the entire range. And therefore, it's important over the next decade to be prepared to start many more projects if we want to cover the entire QCD axion range. And let's see, so there were arguments about it. There was a gap. Yeah, this is a pretty gappy right here. There's perhaps Ariadne might get up to there. But in general, there's many ideas out there, and if you take their optimistic or some sort of Monte Carlo sampling of what mass range they think they're covering, it looks like we can do a great range of what's out there if only we can get these techniques developed. Yes.
I've looked at this plot many times, and I never noticed at the very bottom there's this magical next-gen ultimate axion facility.
I'm going to talk about that at the end of the first half of the talk, right? It is entirely mythical and mystical, but it's
great.
I'll give you an argument for that, right? And we put it at the bottom because it's not supposed to supersede anyone. Right, and the intermission is at this town hall. I then went off and talked about these dark matter new initiative projects, ADMX. You're going to hear. I mean, that's my second talk, so there's no reason for me to talk about it twice. DM Radio. Chelsea Bartram's going to talk about that at towards the end of the not this session, but the end of the conference. So there we then went in to suggest how would a funding agency get at this. We liked there's issues that very large projects accumulate more and more money and their cost overruns. In one of their cost overruns, you could fund development of 3 of these. And so there's much push from the community to say, hey, you need to sequester money out specifically for these relatively small projects and developing techniques to reach the QCD axion at non-standard masses. We had a list of example projects that have US ties here. And I should mention, if you get left out, you often say, oh, if you get left out, then you all come to me and I'm sorry, and it was unintentional. In this case, it's because it was directed very precisely at US funding agencies. If you get left out, it may have been because you didn't have you weren't looking to ask for money from the US. But if we miss something, then let me know so I'm aware of it. And it's important that while we marked and said, look, the QCD axion is a flagship wave-like dark matter candidate. It is something we have experience in looking for. We have plans. It should be funded with this it is not the only thing out there. There are vector candidates, there are scalar candidates, and they both need strong stories. So they need theory support for understanding what are the consequences of these, what's the best motivated parts, what are less motivated parts, and as well experimental techniques. In fact, but it turns out we could get a lot of experimental techniques that could have sensitivity to a wide range of masses and frequencies. And they're almost really good experiments in search of a good theorist to tell them what exactly they're looking for. And so we pointed that out as something that needed to be supported and was useful, because it could be you get a signal in anything like this, and it's important to be able to interpret exactly what signal to look for, and if you see a signal, what does it mean? Okay, now so getting to the mythical center. So the Axion program has a lot less funding than the WIMP program in the US. If there was more money, how would you spend it? Would you dump into one project? And we made the observation that many of these experiments, not all of them, but many of them kind of live or die on the size of their magnet. And by size, I mean just raw stored energy, V squared V. And I can point out many of the experiments, magnets I've been trying to label sort of what frequency they have and what sort of stored energy in the magnet, and point out that as we move forward in experiments, the bigger experiments that are DFSE sensitive get way high up on this chart, and the next generation experiments proposed get higher and higher. And so this suggests there's shared infrastructure that's needed in many of these experiments. They need big magnets, big V squared V. Now they may disagree about exact geometries, but if the magnets exist, it's possible for the experiment to accommodate where it could fit. They need people with expertise in cryogenics and quantum sensing. And just pointing out that the US has these national laboratories, they like to put big investments in infrastructure if it means that gets money to their state. And so any national lab that decided we're going to start an Axion center and we're going to build a big building, we're going to get a lot of magnets, we're going to get cryogenic support, we're going to get helium liquefier, would be a natural place for many of these new projects to coalesce around. And so that's why I put that in the end, is to say that a national lab with dreams of grandeur could put the money down and attract enough experiments to cover the whole range. So regardless of whether you agree on the truth, it's a compelling story to the funding agencies. So one other thing we did is kind of a fun exercise, since we were talking to the rest of the physics community. Why should they care? What would a discovery of dark matter mean, aside from, it's important to us. But one thing we realized that wasn't common knowledge is if you make a discovery, let's say you get here, this is sort of the classic haloscope range. So we have a QCD axion that's after inflation. So we're making judgments about when inflation happened. If you're living in the KSVZ or DFSZ line and you find an axion, there's kind of this dirty secret that you now know that there's either an expanded Higgs sector or additional quarks. And the people who run the big accelerators get very excited if you could promise them. You promise them there's another Higgs out there. They like that. So that was important to share. And then of course, it's a discovery in a haloscope is insufficient to know exactly, is it QCD, is it not really QCD? But that implies there needs to be a lot of investment in figuring out how to get at these nuclear and electron couplings. And then there's also the fact that almost any of these discoveries use the line shape and you're doing axion astrophysics. So you have consequences for people who do astrophysics who don't really care what the dark matter is made of, but they are kind of interested in what the local virial velocity is. Much lower down on the QCD axion, this is probably before inflation. So now you're having something where you actually have a probe of stuff going on before inflation, which is rare and exciting and interesting. It is a suggestion of new physics at the gut scale. Once again, you're either a Higgs sector or additional quarks. There might be consequences for the CMB, and then the others hold true. And there's always the possibility that one of these experiments discovers something that's not the QCD axion, something falls off the line. And this is what higher order theory that you talked about strings. There we go. So this would be very exciting because it means that there's still a lot of theory work to do because the vanilla QCD axion is not sufficient. This is something higher coupling. So I then left them with these, exciting promises of discovery and what would the consequences of discovery been, and to say that there's a lot of people interested in wave-like dark matter. The QCD axion is an accessible and target over the next decade and should be on the radar of funding agencies. We have existing experiments that are probing interesting regions of QCD dark matter, and they should no longer, they're sort of on the runway and they need to be given permission to take off. But that's not sufficient by itself. There also needs to be support for R&D programs to expand the mass range, other techniques, scalar and vector candidates as well. So, yes.
First of all, this was obviously a huge investment of your time. So many, many thanks to you and Lindley and Jorg for doing this, because it was 2 years out of your life during COVID. Question, normally the snowmass process happens, if not with coordination, but at least with cognizance of, for context, the European process, which typically was phase shifted by about a year. What do you know about the European process for their cosmic frontier, and what were the implications for the US program?
Ooh, yeah. So the sad fact is very little. It was during COVID, everybody got phase shifted in different directions. The European process went one way, we went another way. The astrophysics went somehow yet a third way, even though time is only one dimension. And so I don't feel that this time it was as well coordinated as it has been in the past. Just that was the fact of life. So this is a good time for questions, since the nature of the talk changes dramatically.
I'm just curious, I've read recently of these proposals to sort of use haloscopes as gravitational wave detectors as well. Is that something that made it into SNOMAS at all, or is that a way to sort of crosstalk between funding agencies because all these things are semi-segregated?
So this is something this is about haloscopes, gravitational waves. So this is something I'm super interested in. It came out late in the SNOMAS process, and it didn't quite work in for mostly the reasons that you're talking about. And so far, from my very limited knowledge, I'm excited about this, is every time I've talked to someone who does serious gravitational wave astronomy about the sort of gravity waves I could look for, because this is like, going to my second talk with ADMX, they've scoffed at the possibility of these sources, which doesn't mean that it shouldn't be done, but it meant that it would be hard to put a cohesive story to say this is a priority. So it's perhaps if you can give me better motivation, I would much appreciate it.
So there are a few papers out there where people have some ideas about using axions for like submarine communication and things of that nature. I don't know if that's worth using as motivation if you're talking to the government.
So that's it. Carl, didn't you write this paper? Yeah, what I can say is about this process is it's not all funding agencies, and it's within high energy physics cosmic frontier. So this is very dark matter centric, right? Like there are people who we've had many talks about axions in contexts where it doesn't have to be dark matter, and that actually fell into other subdivisions. And practical. Fortunately, it was all science all the way down, and so we didn't have to reach for practical applications. But yep, it's any story you can tell. I often tell people that when I find axions, I'm going to put them in a bottle, and they probably make your teeth whiter or something. You can't prove it's wrong until you found them, right?
Okay. Do we have to thank for the first talk?
You don't. No. Let me just do it all at once. Okay. So let me change gears. So having talked about all this snowmass process. Let me talk about an actual experiment, ADMX. I'm representing a far smaller group of people here. Here's the ADMX collaboration. We've been growing rather steadily over the last decade. And so we're planning on finding the axion. There's an American expression, or maybe it's a Seattle expression, to drink the Kool-Aid. This is where you buy into the company has a statement. And it's many people like, that's what the company, but no, we believe we are looking for an axion, and this is how we're going to find it. Right, and we're using the haloscope. Of course, I suppose has somebody shown this, we haven't shown it this week, right? So I have to start from the beginning. I assume that most of you know this. You have the magnetic field, you have an axion, and the axion's wavelength is long. We draw, once again, we sometimes draw this like a particle coming in, and that's to help the people who do accelerator physics understand. But we all know this. The axion, it's a radio wave, right? And inside this magnetic field, there's an E dot B coupling such that the axion mixes with photons, and you can capture these photons with a microwave cavity there. So many of these are soda cans, though we're going to hear much more interesting geometries in a very short while, probably just later today even. And so if the resonant frequency of a particular mode inside this cavity corresponds to the photons that axions are mixing into, then you get a resonant enhancement of axion to photon conversion, and you can pick these photons up with an antenna in a very simple way. And if it's not quite the right frequency, then you don't quite get resonant enhancement, and so you do some geometric modification of this cavity until you get the right frequency, and then you get resonant conversion. You pick that up, use a very, very small signal. The characteristic size of these signals is octowatts. So down at, it's not quite, it used to be the bottom of the SI unit scale, but they invented a new prefix that's 10 to the minus 3 lower. So the signal gets amplified, and you look on the, in a background of noise, you're looking for a bump, excess power. So power coming from, well, apparently nowhere into your cavity. And that's the signal of axion dark matter conversion.
Right. The first statement is false. May not be correct. You don't know that it is exaggerated.
That's fair. That's fair. Well, yeah, that was in the context, right? Because you don't know my noise temperature either, right? This could be terribly high noise, and then you have to exaggerate it. But that's a fair point. This slide came from when someone was being very precise about whether they were using what fake signal on what real data. But it is important that we've seen that things just below CAS, axion-like particles, would be really quite large signals, and some of these very high densities, Pierre's high density things, some of them they get to the point where they break your amplifier if they hit. So that's kind of interesting, but not for QCD axions. That you expect a small bump and a small amount of power. When building these experiments, you want a big signal and you want small noise. So you want large volume of cavity or cavities, it's becoming, to convert more dark matter. You want a high magnetic field. You want a high cavity Q. You want the cavity to be very, very resonant and tuned directly onto the axion. That all get you a bigger signal. And then you get to make your noise small, you want to eliminate cavity blackbody radiation. You want to cool it down as much as possible, and you want to eliminate all possible noise you can from the amplifier. So let me talk about how we address these issues in ADMX and the design. So the left-hand side is a rendering of a cutaway view, very, very old one, where we have that's a magnet. It goes up to nearly 8 Tesla these days. Inside is that cavity where the axion photon conversion happens. Inside of that is a lot of refrigeration to get that low temperature. Then we have this whole separate magnet, and that's because when we say we want to lower the noise of the amplifiers, the lowest noise amplifiers in these frequencies are things like Josephson parametric amplifiers, traveling wave parametric amplifiers, these quantum amplifiers that you hear the people who do qubits talking about, and they're all at millikelvin temperature. They all work on superconductivity, and they all hate magnetic fields. So you have to have this entire cancellation systems and shielding for your amplifiers. And that's what's going on there. This section you pull out and work on, you'll see several pictures of that. And that's one case. I can tell that this is the time it's being dropped into the magnet, because if it's coming out, then it's cold and frosty. So I mentioned tuning. So as we'll start from the bottom, I guess, so we're talking about the cavity. This is what it looks like if you take the top off of the cavity. So right circular cylinder, and we've got these tuning rods. In this case, it's 2 rods, copper coated, and they rotate around, moving it from kind of an empty cavity structure to coaxial structure. And this changes the spectrum of modes inside the cavity, changes the frequency. And since the Q is quite high, 10 to the 5 perhaps, you have to be really tuned right onto the axion mass. And you tune it by moving these rods, and here's a plot of frequency versus rod position. And so you move the rods from the edge to the center and back to the edge. There's many modes. Not all of them couple equally well to the axion. In fact, it's the lowest one in general that couples well to the axion, and that's the mode that we track. And so this is very much like an AM radio where you're tuning, listening for that excess power. Talking about the noise, this is maybe a characteristic just signal and noise plot, but this is what you're looking for. Is you're looking for a bump, and you have a whole lot of this. It's very fortunate in the field of axion searches. Our noise is, for the most part, thermal and very well understood. If you just histogram it, it looks like this beautiful Gaussian, so out to many sigma. And so you have to understand that very well. But it's fundamentally a temperature you're measuring, and it's not just the temperature. There's other things. There's how much extra noise are being added by your amplifiers. Turns out that that ends up looking thermal, even if it isn't truly thermal. You have to understand all the losses in your system, just how much is this signal getting dropped down every time it passes through a cable. And what you end up doing is you calibrate what's called your system noise temperature. What's the equivalent black body radiation temperature to make this stuff? And then you use that to judge how big your signals are. So this turns out to be a lot of the work we spend in the analysis of an axion haloscope and an ADMX. Here's an example showing our the cold RF is what we call this. You see it's this mini lines. What's important here? So there's a cavity down here. There's a big mess of things that we have to understand. These amplifiers, how much noise they're adding, how much loss is going in here. And we have this is our heated load that has a little heater on it and a little temperature sensor on it. There's also temperature sensors here. And we can heat this thing up and down when you switch to look at it and look at the power coming out. So if you talk about what's the primary noise, what's the primary calibration of how much axion power I get, is that someone at NIST makes a temperature sensor standard. They talk to the company that sells these calibrated millikelvin temperature sensors. I buy one of those millikelvin temperature sensors and put it here. I heat and cool that temperature and measure how much power makes it coming out. And that tells me all of these, Boltzmann constants, gains, losses, all of that is encoded in this. And you can see it's very linear in a very sensible way. And that tells you what your noise temperature is. If for those of you who in the know, and you're like, well, it's not really the noise temperature, it's the noise temperature divided by the loss. But yes, that has to be incorporated too. That is the first stage in understanding. It ends up getting to the top of the calibration. But you can bootstrap off that by turning on and off your quantum limited amplifier or near quantum limited amplifier, JPA. So we use this Josum parametric amplifier. It's great, very low noise. It is also very relatively narrow in frequency response. It's got a kind of a megahertz bandwidth that it operates. That's fine. The cavity is only 10 kilohertz, but that means we have to look at curves like this. So that's a current we put on it, and this is a frequency. This has to do with phase, but the important thing to know is that we have to drag the operating point of the JPA across here to match our cavity. And then once we do that, we can look at what's the gain versus frequency. This is, about a order 1 to 10 megahertz. And we look at how much power, has to do with how much the power drops or lowers when you turn the JPA on. And you can use this to infer a total system noise temperature as a function of how close you are to the center. And so that is the path from a temperature sensor all the way to saying, we know it was this many octawatts, and that's why, and then from the octawatts and the magnetic field and the volume, we can tell you a GA gamma gamma that we're sensitive to. So operations, this is a plot that we look at operationally, is you're sensitive to only a narrow range of frequencies. You move your sensitivity range by tuning those cavity rods. You make power spectrum after power spectrum. These are separated and don't use this as saying, oh, this has more power than that. This is just taking a whole bunch of power spectrum and then stacking them on top of each other to give you a feel of how we scan across frequency space. And if you have, this is a synthetic signal, by the way, if you have a signal, then as you get to where that signal is centered on your cavity resonance, it gets bigger. And then when it goes away, then when you do tune off, it goes away. And so you have this ability to tell what, the signal is coming from the cavity because it has to do with resonance. To give you a feel for numbers associated with this. Each one of those spectra you saw is about 100 seconds. It's about 50 kilohertz wide. We usually, let's see, so if you are at a nominal scan speed, you're maybe spending 10, 20 minutes at any one particular frequency take one frequency to go from one side to the other. We break things down into 10 megahertz if we're feeling aggressive, maybe 20 megahertz, and we go across it once and then look for bumps. And then there's this whole procedure to go through to deal with bumps to understand, okay, was this an axion signal? Was it someone had a port open and had their cell phone beside it? Was it just a statistical fluctuation out? I don't know if I'll walk through the whole thing, but there's a lot of measuring. Does it persist? Because this is an important thing, is that we make this assumption that axion dark matter is relatively uniform, homogeneous, and time persistent, so the signal's always there. Those of you who are talking about short time, a clump of axions coming and going, this is very hard to detect with our apparatus, and those signals are by default discarded. So if you're interested in that we can talk and think about ways to develop it, but in general, the whole thing's built around a very persistent long-term signal, because almost all the other human-made noise that leaks in is not persistent. It comes and goes. Let's see, finally down, and then so down here is synthetic axion injections. So, oh yeah, now we should turn off the synthetic axion injections. So it's a fun story, and I like to tell it because we have kind of what is this, like red team, black team. We have one of our collaborators has this instrument rack, and it's sealed and it's locked, and usually I don't know where the key is. And it's covered, it's all taped over in the front, so you can't see what the instruments are doing. And there's a cable that comes out, and that cable runs to the bottom of our cavity into a little antenna. So it's injecting, and from the point that antenna has an RF signal, it is indistinguishable from something that came in to the cavity, an axion signal. It's okay, indistinguishable. This turns into a battle between the injectors and the analysts to see if it's actually indistinguishable. But the idea is, when we were running, do we have candidate signals? Yes, we always do. There's always these synthetic injections. We're always on edge thinking, this is it, maybe this is the one. And so only after we have passed all of these checks do we go and say, okay, look, it's time to do some major operations, many months of turning the magnet on and off and starting to write the paper. Do we get the signal turned off? There's several categories. The big ones where it's about to write a paper, those are really only allowed to happen every year or so. In any 10 megahertz, we get 5, 6, 7 that are just test signals to say, okay, I found this, and they say, yeah, those are the ones you're supposed to find, turn them off, go back, continue. Here's an example of one of the synthetic signals that was kept secret till almost the very end. Some plots made by the analysts. Let's see, this is talking about what is the exact line shape. And this is the analyst trying to decide whether it has exactly the line shape that you expect from an axion. And this is fun to do, but at the same time, it's not the line shape. You can assume a normal Maxwell-Boltzmann distribution, and that's about the most conservative thing that you can have. But as Pierre told us yesterday, they could be much, much narrower. And so this isn't this isn't a deciding factor in the axion. It's just a matter of like, what are we looking at and getting a feel for what kind of axion it might be. In this case, it was a little bit narrower than what we'd expect from the most generic Maxwell-Boltzmann. This is a measurement. This is mapping the cavity resonance from the power of this mysterious signal, showing that yes, it indeed follows the cavity resonance, and that says that it's it's like that movie where the calls are coming from inside the house. You don't get this unless the signal's coming from inside the cavity. Yeah.
So this looks super impressive. I just noticed the chi-squared per degree of freedom is actually not great. 717 per 229. Is that something I should be worried about or?
you know, I violated that rule of don't put anything on your slides that you don't understand. I don't know. I have no idea what exactly the analyst was putting that in, because it's like, this is an amazing fit and that looks like terrible, right? So what's the deal? I don't know. Sorry.
No worries.
Okay, and then this is when I said, you know, it's indistinguishable when one of these synthetic signals goes in from a real axion signal. Here's a case where the analysts working with the operators, because it's unlike experiments where the operators run, and then there's a big data set and you analyze. Because you have to go back and revisit candidates within a week, the analysts and the operators have a huge amount of overlap. And so the analysts are getting back to the operators within days saying, please do this operation, please. And sometimes they're the same people. And so in this case, they thought it would be fun to look at different modes. I told you before when I showed you those modes tuning that there was really only one great axion coupling mode, and then the rest of them coupled either less so or not at all. So in this case, was there a question? Oh, in this case, the TM010 is the lowest mode. It couples well. If you know about the E.B coupling, this couples very well. You can see the integral over this is non-zero. The TM011 does not couple well, and the integral over this is 0. And so axion signals would be big here and non-existent here. And the analyst told the operators to scan the system so that and switch which mode they were monitoring from 010 to 011. The signal was bigger in the 011 where it shouldn't be. And so the analysts called up the synthetic injection team and said, gotcha, because the synthetic injection team wasn't paying attention to what mode was in there. They didn't have the, you know, that wasn't in their software to expect. So anyway, it's a fun story to tell, and I like to tell it to show that this is like, what we're doing is we're trying to find the axion. We're looking at signals all the time.
May I comment on this? The most fundamental way to reject a signal is to scale it with a magnetic field. Even for that, you have to take data for a long time to establish stability. So we need to be doing those things so that otherwise we'll miss it.
That's absolutely right. That is you on our checklist, that is the last step. And the reason it's the last step and not the first step is that scaling for our particular magnetic setup, it's a big deal because we have the JPA shielding magnet and the main magnet are not connected except by software. And they ramp down, they ramp down tick, 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 tick together, but it perturbs the amplifier. So you'd have to ramp down, you have to wait a few days for the thing to settle and rework the cancellation and then take data again. So it's a rather big time investment. However, you're right, that's like, you know, if someone doesn't say, oh, I found it, if you go, I found the axion, and you don't show any magnet off data, or you don't show it scaling with B squared, don't give that talk. Like, just go back and take that data. That's the most important thing. I agree. Okay, so having talked about how we look for signals, if we do not find them, we are forced to set exclusion limits. There are exclusion limits as of, so that's we had a paper in 2021 showing the range we've covered here from 2.6 to 4.2 micro EV. On the left, we're talking about assuming some nominal dark matter density 0.45 GeV per cc. What models can we exclude? We aim to exclude DFSZ. We do so over much of the range, though the pandemic hit us and we had extra noise and we weren't able to fix it for a very long time. So we've got some range. The dark, this is a standard Maxwell-Boltzmann is the dark red. There's a pink here that talks about, well, what if, what about different, gives you a feel for what if we had narrower models, we had colder axions. But the true one to look at is the dark. You can also look at it as saying, oh, suppose that I knew the axion was the standard KSVZ benchmark. What sort of axion dark matter am I probing? And you can see for KSVZ, you're probing down to where axions are not all of dark matter. They're not even half. They're a little less. And so that gives you a sense of what we are sensitive to. If axions are out there at 10% dark matter, even KSVZ, we are not 10% at KSVZ, we're certainly not able to probe that. That's a much bigger experiment. So maybe that's what we have to do. Talking about what's upcoming, what's in preparation, the data is taken, the papers are being written, preliminary data that's been shown. So over the last summer, we ended up having this pernicious leak that there was a lot of work with cryogenics, and we were able to get it running again last summer and demonstrated we can get lower noise temperatures and able to recover some of that DFSZ region, though not all of it before our clock hit to where we had to do the next thing. So here's once again axion photon coupling versus frequency. So we took a chunk here and pushed it down to DFSC, a chunk here that pushed it down to DFSC. In this case, to give you a feel for how often do we have synthetic signals? How often do we make a discovery or think maybe we did? These red dotted lines are synthetic injections, synthetic axion. I forget, synthetic axion generator. That's what it stands for. And there's also how often do we hit radio frequency interference that kind of trips up the process and requires us to do another step. Those are the gray dotted lines. So you can see that it's not full of radio frequency interference, but it is something you have to deal with. So I think I saw some questions. Yeah. Oh, he's got to give him the mic.
So do you know what local dark matter density you assume for this?
This is 0.45 GeV per cc.
So what if, from astrophysics, values as small as like 0.25 GeV per centimeter cubed are allowed. So suppose that we got unlucky and the dark matter density was lower. We also had a DFSZ signal strength and we're sitting at like 800 megahertz. Would you guys flag that in your rescan, or would that signal be too small to not be flagged in your rescan?
So, okay, so you're asking a very delicate statistical question, right? So when we say we exclude a region at 90% confidence, there's many, Chelsea's smiling because we have a lot of discussions about this. So we're saying that supposing we see an excess in our experiment, but it's not sufficient to say this is a signal. And when we run the experiment again, 90% of the time, we won't get a number higher than that, which is that ends up being a very well-defined statistical question. And it's of no interest to you whatsoever, right? This is an experimentalist repeatability thing. But it's not quite the same as saying, oh yeah, if I run this experiment up 10 times, 1 out of 10 times I miss an axion, which is a bit harder to do. So the answer is maybe, it might get flagged, especially you can see how in some of these, if our Q is jittering or our rods are skipping a little, you get little pieces where you have very, very good sensitivity and then not good, very good, not good, and we end up having to draw the line at the worst case. So maybe, but you can't be sure.
Yeah, I guess what I'm getting at is like your G gamma gamma probably is degenerate with your dark matter density, like the square root of the dark matter density. It's probably like G gamma gamma square root.
Yeah.
So if the difference between like 0.25, 0.29, like 0.45 when you take the square root, like that's sizable on this figure. And I wonder if there's like any discussion to take a more conservative dark matter mass when you're scanning, just so that you don't miss it with a lower dark matter density.
So if you want to get half the dark matter density, you scan 4 times as slow. So if you were proposing, say, a 10-year program, you're now proposing a 40-year program. And so is it better to scan shallow but wide or deep but slow? So if I pick, so at your level, so unfortunately, just like where does the technology fall right now is if I pick deep but slow, I'll be dead before we can scan our accessible region. So instead we pick a shallow but wide because we think that's the best discovery potential, even though it's not at the most pessimistic dark matter density, right? And then if I did 0.25 GeV per cc, someone would come along and say, well, DFSZ isn't actually the most possible pessimistic. I can tweak the cancellations. You should really scan, 10 times more, and there's the slippery slope, But it's, I don't want to say that it's, I try not to use the word definitive because it's, if we don't find the axion, probably someone will have to build something better.
Okay.
Yeah, you're right. Because GA gamma gamma times the density is our limit, really. But that has nothing to do with the axion, whether or not it's there. Because locally we look for a signal. And that's the answer. It's just what you just said. If you change the density, these limits will move up and down, but that's the best we can do.
Maybe I'd counter with, you get an astrophysical hint with a mass to within 1%, and I'll drop, I'll do an experiment that drops down by, you could do a order of magnitude, not quite 2, but so yeah, these sort of limits you get with 20 megahertz at each frequency, or sorry, 20 minutes at each frequency. If you give me an astrophysical hint, I'll spend a year. So whatever the square root of that is, I can improve it.
Just to clarify, my only concern is that 0.45 seems like pretty high, and DFSC is pretty motivated. So I'm just like in the back of my head a little worried that we're going to scan, exclude that space, and actually it's going to be there, but it will just, bend down by a factor 2.
Oh, yes. So maybe so here's the thing that bugs me as well about the historical presentation of these plots, right? Is that historically we make a dark matter density assumption, and then on this y-axis, we tend to say, oh, here is the coupling, when it's really coupling times root dark matter density. And so when something is excluded, that's what the dark matter density.
0.45 was the latest Gaia, isn't it?
Yeah,
Well,
yeah, that's
you
the thing,
think
right?
it's large?
I think it's
Very large uncertainty.
yeah.
Yeah, but
And the vertical acceleration of stars, so this tracing that is quite tricky. So you're right, it is around that number, but there's a lot.
If you imagine, grad students are like, working their fingers till they bleed to understand a 5 or 10% uncertainty on our noise temperature from the amplifier, when fundamentally you make a plot where there's an astrophysical uncertainty factor of 2. Yeah, it bugs me, but what can I do, right?
I mean, if you have a better recipe, we can try to agree to another number.
Yeah, I'm starting to like the plot on the right better, but
That's the real.
okay. I'm dragging on. Let me continue. So I showed you that that's a paper in preparation while we decide exactly where that falls on the y-axis. What are we doing right now as of February 2023? The kind of our timetable said, all right, we spent as much time as we said we were going to in this this frequency region. We need to move up, and there have been people working, offsite collaborators working on the next generation cavities, the next generation JPAs, and so we pulled that out and began to refit. Here's just fun pictures of the team there. So that's an experiment that's just come out because it's still frosty. There they are ripping it apart, and we're going to replace this thing. We're going to replace the thing up in there. Our target range is 1 to 1.4 gigahertz with a single rod system. So they pulled the rods out. I think it's one of these big rods. This is about as far as we can go with a single cavity system with our current setup. So I've been in there putting cables in with my students. And so that is to say we've been working in this region. We're going to move up here. And it is important that I note that this is the first time that there's competition. Giannis, you will tell us how you are already operating in this region. And so this is a reason for the Axion community to be excited, is that now we're racing to see who can cover the most of this. How much will we overlap? How much, certainly if there's 2, we shouldn't leave any gaps. And so that'll be really, I think it's going to be a really exciting year. Because we haven't turned on and there's already regions excluded here. Beyond that, the next upgrade, I don't know if it's obvious from this picture, but that's 4 cavities of half the radius. We are going to move to a multi-cavity system. We need to add the signals from these cavities in phase. There's a procedure for doing it in analog. There's a procedure for doing it digital. We're kind of, both methods are coming to a head. The analog is currently the one in the baseline, but there's other possibilities. And that should get us up to about 2 gigahertz in the next run. At that point, for ADMX as it's built, it gets very hard to go much further. The cavity Qs tend to drop. The quantum noise, the standard quantum limit, which I haven't talked much about, but even these Josephson parametric amplifiers fundamentally always add a half photon of noise, and the photons get heavier as you go up to higher frequencies. And so the effective temperature goes up. We need more oomph. And so how do you get more oomph? I guess 5 years ago, it was like, well, it's not clear here are directions that to pursue, but individually, people have achieved each of these. Is you can get a bigger, higher field magnet, that's just money. Larger volume magnet, that's just money. Higher Q cavities, a lot of work by mini groups to get mildly superconducting to very superconducting to mild Q increases to extreme Q increases. More sophisticated cavities, so things that are not just these soda cans that we've been looking at. And then things like squeezing or more exotic things get below this quantum limit. We are positioning the next generation ADMX to utilize basically the minimum number of these required to reach the next frequency because we're trying to get reliable performance. But regardless, we're certainly starting with a magnet and then trying to incorporate what we need from below. It's called ADMX EFR, extended frequency reach. And our goal is once again to make a discovery. And in our minds, that means a continuous scan upwards at DFSC sensitivity. Here is the design that we have come up with. It's very different than you see the normal haloscope. We're going to try and separate out these quantum electronics get fancier and fancier, and so we're going to pull them out to their own fridge. We have a horizontal magnet in mind where we can put the resonators, and it's no longer just the resonator, it's a resonator array, because this is the brute force approach, right? You've got a big volume, just pack it full of resonators until and coherently combine them. So the magnet is in existence. It's near Fermi National Laboratory. We believe we'll probably try and get, we've got a site there. And the idea is that eventually the system would move from University of Washington, where it's currently operating, to being at Fermilab. Though I guess it's the heart of the experiment moves, because it's the magnet, of course, we'll be using this new one. It's not hugely stronger, but the B squared V is significantly larger because it's just a big MRI. So when I talk about cavity array, this is the sort of a Swiss watch design where we get these cavities. They're not hexagonal inside, they're round inside, but they pack nicely. And we've done many studies to talk about if we combine these and we look at this is talking about volume of the magnet combined with these numbers represent how well the axion wave function overlaps with the photon wave function side and what kind of performance can we get. And then how are we going to deal with, these are mode crossings, that if an axion coupling mode to a non-axion coupling mode are at the same frequency, it's not obvious what your sensitivity is. And so we're dealing with those probably with slightly different shaped cavities. So those have been, prototypes are being designed. We're working on the readout. This is now talking about multiple quantum amplifiers, which some time ago would have been silly to suggest, but now if people are building, 100 qubit systems, they're 18 JPAs, no big deal. That's what they tell us. We'll see. And so to talk about where would we be going, so this would be the 2 gigahertz that I said we were going to do with the existing ADMX infrastructure, and the next step would be up here. And that would be the first step of continuing to scan up and continuing to add these new advanced technologies that are being developed by ADMX and many other groups all over the world.
What's the time scale?
Ooh, difficult question, and because it's the limiting factor on when this thing moves to Fermilab is sitting on the project is sitting in this dark matter new initiatives process, and we need to be given the go signal. And I believe it is it's 3 years from the go signal to first data. And you know, they could do the go signal this fall, but I don't, they've been shaking their heads about the program for this year, so it's almost certainly not. Oh, for 2 gigahertz? Well, honestly, Giannis, we had 2 years planned for 1 to 1.4, but odds are it's going to be 1 year because you're going to do at least half of it, right? So that means that we should be starting the multi-cavity system in 1 year, and then it's probably 2 years operation, 3 years operation there. Right. Okay. Am I dragging on too long here? I just have a few more slides to talk about what goes beyond ADMX, ADMX EFR.
You're going to have 18 JPAs? Sorry.
Yes.
So for each cavity.
Each cavity gets its own
So
JPA.
they are not connected to the same. They
yeah,
are read out independently.
There's all sorts of good reasons to amplify and digitize each signal separately and then combine digitally. Like this is how the radio telescopes do it. Modern radio telescopes do it. Is there's games you can play with axion interferometry that get you a little bit. Mostly it turns out to be quite challenging to maintain analog combining while you're tuning frequency.
Yeah. But then are you still coherent in for the power?
You have to combine them coherently digitally. That means there's a magic phase in which you combine the voltages that is coherent. And you have to measure and know that phase. But yeah, this is like radio telescopes where they can do interferometry with multiple signals digitally. Yeah, well, that's an interesting question. Do you have to? Yeah, you ought to. I would say you ought to. I don't know if you have to. Yeah, it would be foolish not to. But
that's phase dependent. So in principle, you have to use the same phase.
Yeah. So moving beyond, I've talked to you up to 4 gigahertz, I guess, 2 to 4 gigahertz. We're also doing R&D within the collaboration of expanding this. There'll be the old ADMX magnet. There'll be space in this ADMX EFR magnet to explore further frequencies. So we're looking at dropping down to lower frequencies down until we meet nicely with DM radio. We're looking at options to reach beyond 4 gigahertz, 6 to 8 gigahertz with some very interesting resonator designs that are tuned in interesting ways. I think this was talked by John Paulo Colosi last week. I don't have time to get into it. And then we have some ideas for multi-wavelength resonators. We have this 18 gigahertz apparatus at UW that my graduate student put together. Looking further beyond that, coming back all the way back to where with this scheme to get a national laboratories interested in shared infrastructure, there is an attempt to persuade places like Fermilab to have a dark wave laboratory. It's to the point where space in laboratory buildings is being looked at, pitches are being made. So ADMX EFR takes this space. There's a lot of extra space that if say Fermilab can be persuaded that there could be space for users or additional collaborators to do, cover more of the frequency space at once. So some of you, as we make progress, I may reach out to you as potential collaborators or say, hey, would you use this space if it was there? So that's where we're trying to look, look to the future as we're doing this and try and get the whole range. So to wrap up, sometime in the past, recently in the past, we changed axion haloscopes from being an instrumentation development exercise to we are building these things. We're looking at where we think we ought to look. We think we're going to make a discovery. So they're now discovery machines, and someone said in the last talk, yeah, that's weighs heavily on our mind. ADMX is operating at DFSE and near DFSE sensitivity over a promising frequency range, expanding that every year, and we have plans to implement ADMX EFR, which will continue to expand that. And furthermore, we're trying to work with, we're working with the community to scale things up and turn this into an industry where we are working with the right sensitivity to find the QCD axion, because I think it's out there. So thank you very much.
Thanks for the really nice talk. So you talked about your plan to go up to higher frequencies, but it seems like there's going to be a very small gap between DM radio meter cubed and the bottom of your limits. Is there any thought about you guys going lower in frequency to cover that gap in the future?
So you're saying a gap below this?
A gap below, oh,
Absolutely not.
oh,
I've been,
good.
I've,
Oh, I
I've,
didn't
I've,
see that.
I've,
I
I've,
see. Okay, I
I've
missed
worked with
this.
my colleagues at DM Radio
That
that there's a
covers, yeah.
line in the sand. And we've gone up this far and
Yeah,
they've
yeah.
gone up this far. And so we plan, we've been careful to coordinate on that.
Yeah, sorry, I didn't see that.
Yeah,
Understand.
Yeah, and when will this actually get implemented? I'm not sure, but yeah,
Okay.
it's, we don't intend to leave a gap.
Okay, so that's been coordinated.
Thanks for the talk. So I'm interested in the multi-cell high frequency setup. So in that setup, you have a smaller cavity so that each of them is sensitive to a higher frequency axion mass. So then you take advantage of multi-cells. So my question is, how does the signal power or SNR depends on the number of cells when you coherently combine the signal from them? Like I was actually told by the colleagues, it depends, it's linear to the number of cells. So my question is like, since axions are coherent over all these cells, so the wavefront is static when they pass through the detector. So like it wouldn't be able to resolve this like number of like this array. So I wonder, how do you get the linear dependence on the cavity number? Does that question make sense?
No, that question makes sense. Let me see
Yeah.
if I can put it in the, so if you look at the total axion conversion power in a haloscope, there's this volume term. It's linear with volume. If you get, twice as much volume, you get twice as much dark matter in there, you get twice as much power out. And so with this multi-cell system, you have to, if you combine them coherently, it's like just expanding the volume. And so it's linear with the total volume, therefore linear with the number of cells. If you do not combine them coherently and just say, I'm just going to measure the power and add the power, throw away the phase, then you only scale as a square root of the number of cells. Is that the direction you were?
That's, yeah, so that was what I was told as well. So like, but then there's this Q factor. So if I understood correctly, Q is to do with the lifetime the photon spends in the cavity. So usually if you have a larger volume or like a cavity cell, you spend longer time in that cavity. So
I see. Okay, I see what you're saying is that smaller cavities tend to have lower Qs. But once you've got one cell made with a certain Q, if you double that, you don't change the Q usually, unless so Giannis, you're going to show the pizza cavity, right? I think maybe when you show that, it'll because that's a very, it's straddles between true multiple cavities and one cavity split into parts. That may be clearer when you see some of his cavities.
Yeah, actually, it's a question I had on limit setting procedure. So I think it's the Haystack collaboration that is employing a more like Bayesian-inspired approach. And I think recently there was a paper by Sada Algeri, her student, I guess, and Jan Konrad about different approach to modified approach to the frequentist way of setting the limit. So I wondered if you or the collaboration has a view on this, or what your thoughts on, if you're familiar with the proposal.
So it's discussed a lot within the collaboration. It continues to be discussed. There's a diversity of views about what's the best way. I personally go for a very since I'm running an experiment, I want to make the least theory assumptions and the least like things that saying, oh, I need to know my theory prior ahead of time. I'm not sure that the Bayesian proposal is the way quite to do that. And so you notice I had a very careful, when I described my limit, I had a very careful thing. At no point did it ever require anyone to know anything about GA gamma gamma. It required that you measured a power in your experiment and you're predicting the next power that you were going to measure. So yeah, I'd say it's developing and there's a diversity of views.
And the you know, Sarah's proposal, because this is not Bayesian, right? This is, if you are familiar with this, it like appeared in October, I think, last year, like November, maybe, I don't know.
I may not be,
So it's Sarah and Jan Konrad and her student, I think.
but talk to me about it afterwards.
yeah.
I maybe I know what you're talking about and it's not ringing a bell. And to be honest, I don't like to spend a huge amount of time on it. Most of the procedures are about the same and I care about the discovery. The limit setting is kind of the fail case.
Some questions on Zoom, Meter? Okay. So we can go to lunch and we thank again